Okay, exercise 10D, the remainder and factor theorem. A very useful two theorems that we need to use later to solve a polynomial equations, and eventually we're going to deal with differentiation of polynomials, sketch the polynomial functions. So this is the foundation exercise that we need to know. All right, so start with the remainder theorem first. All right, firstly, what is the remainder theorem? So basically what happens is if we suppose that p of x, any polynomial function, is a polynomial, right? And then alpha is a constant, right? Is a polynomial. So we've got a p of x is a polynomial, and then alpha is a constant. So like a constant number, okay? Then the remainder after division of p of x by x minus alpha, if we divide by this factor here, then the remainder is actually equals to p alpha, okay? So what does that really mean, okay? And how do we actually prove it? So I'm just going to start with a very simple example to show you what does that mean, and then I'm just going to go through the actual proof. All right. This is actually a very useful theorem here, so we don't need to do a long division to find any remainders if we divide any polynomials by x minus alpha term. Okay. So for example, if we have this example, I'll start with an example first, and then I'm going to show you how to prove this remainder theorem here. Okay, so if we have a p of x is equal to x to the power 3 minus x squared plus 2x plus 1. Okay, now the question asks us to find the remainder if p of x is divided by x plus 3, for example, okay? X plus 3. Now I'm just going to use two different ways to do this question. The first method, I'm just going to use long division, like what we learned from the last lesson, long division methods, and this way can also, this can also help us to find what's the remainder of this. All right, so we're also like doing a little revision of long division. So we've got x to the power 3 minus x squared plus 2x plus 1. We're going to divide this polynomial by x plus 3. So x plus 3 is the divisor here. All right, so we're going to start the process. That becomes x to the power 2, x to the power 3 plus 3x squared. Okay, now we need to subtract the terms, as you can see here. So that gives us like minus 4x squared plus 2x plus 1. That minus 4x minus 12x. All right, continue the process. That becomes 14x plus 1. And we just need to plus 14 here. So that becomes 14x plus 42. Is that 42? I'm just checking now, okay? Yep, 42. All right, at the end, the final answer is minus 41 as the remainder here, as you can see. All right, now this is the first method by using a long division. If you do everything correctly, you should be able to get this answer here by using a long division. Now the second method we're using is by using the remainder theorem here. Okay, now according to the theorem, that if you want to find what is the remainder if this polynomials px is divided by x minus alpha, then the remainder is just equal to p of alpha. Okay, so that means you just need to substitute the alpha back into the p, all right, back into the polynomials. Substitute alpha equals to minus 3 in this case here into here, all right, and you should be able to find the remainder. And I hope like this actually works, right? So let's just see. We've got px is equal to x to the power 3 minus x squared plus 2x plus 1. Now, if we substitute p negative 3 inside, now the reason it's negative 3 is because we can change that factor into x minus 3. So the numbers we need to substitute according to the theorem here, which alpha is equal to minus 3. Okay, that's a reason. So if we substitute minus 3 inside, we get minus 3 to the power 3, minus 3 to the power 2, plus 2 times by minus 3, plus 1. Let's hope the answer is equal to minus 41. Okay, that's minus 27. That's minus 8, minus 6 plus 1, minus 35, minus 6 plus 1. That answer here is minus... very interesting. Let's see what's the answer here. I don't think I've got the right answer. Okay, that's minus 40. Okay, that's interesting. Where did I make this mistake here? Alright. Very interesting. Okay, so let's try one more time. Minus 27, minus... Oh, yep, I made a mistake. Yes, negative 3 squared should be a 9, not 8. Great, making that stupid mistakes here. All right, no wonder that's why my answer is not right. It's equal to negative 41. That's right now. All right, so it's negative 36 minus 6 minus plus 1, which is minus 41. So as you can see here, it's much easier, if you don't make a mistake, it's much easier using the remainder theorem to find what is a remainder instead of using the long division, going through the entire process here to find out what is the remainder of the answer here. Okay, it's much convenient and fast by just substituting the numbers inside of p of x, and we just get a remainder equals to negative 41 straight away. All right, now the question is why and how this works, right? What's the reason behind? So I'd like to show you the proof. Like why the remainder theorem, it just works, right? It just magically, if you substitute x equals to alpha inside, and you just get the answer. All right, and what is the reason behind? Okay, so the proof is actually pretty easy, all right? Remember, we can actually write down the p of x equals to d of x times by q of x and plus r over x, all right, over x. Now, please remember the d of x is our divisor, and in this case, divisor is equal to x minus alpha. So we can replace the p of x now, or we can replace d of x by x minus alpha times by q of x plus r over x. Okay, from last lesson I mentioned that very clearly. If the divisor is the degree of 1, as you can see here, that's a degree of 1, then the remainder is going to be 1 less degree than the divisor. So in that case, the remainder here is not going to be a function of x, it's just going to be a constant, and then we can just replace a constant r as a remainder here. All right, so once we finish that, we can actually substitute the alpha and replacing the x into inside. Okay, and what you can see is we replace the x by alpha. So we end up with alpha minus alpha times by q alpha plus the remainder. And we know alpha minus alpha is equal to 0. So at the end, 0 times by q of alpha is equal to 0. At the end, you just have alpha r left, which tells you that p of alpha is equal to the remainder itself. And that becomes the proof of this remainder theorem, okay, which is really simple and really easy to understand here. All right, okay, so the next one I would like to talk about is the factor theorem, and this is sort of like more important than the remainder theorem, of course. The factor theorem help us actually to factorize the polynomials into into different factors, and we can use those factors to actually solve the equation of the polynomial function or the equations there. All right, so we'll start with factor theorem. All right, so again, we suppose that p of x is a polynomial, and alpha is a constant. All right, that's very similar to the one we just did. All right, then in this case here, x minus alpha is a factor, just one factor, if and only if p of x is equal to, p of alpha is equal to 0. All right, so what is that really telling you is x minus alpha is going to be a factor if p of alpha is equal to 0. So if the remainder is equal to 0, then x minus alpha becomes the factor of the polynomial expression or the equation. Okay, and yeah, that makes sense, right? If we can completely divide a polynomial function by another another function, then that function itself becomes the factor of the polynomials. All right, so I'd like to show you an example here, and to see how do we sort of do this question here. All right, so example 2. Right, okay, so let's just say we've got a polynomial function px is equal to x to the power 4 plus x to the power 3 minus 9x squared plus 11x minus 4. All right, the question asks you to check if x minus 1 is a factor. All right, so how do we check if this is a factor? Well, again, if we can prove that p1 and p of 1 is equal to 0, then in that case that becomes a factor. Okay, so that's how we need to check. All right, so we'll just check p of 1, which is substitute 1 inside. So it's actually pretty easy, as you can see here. All right, the step you need to do is just substitution and check the answer. All right, 2 minus 9 plus 11 minus 4. Okay, let's see what's the answer here. Equals 2. I'm using my calculator, which I shouldn't. That's really slow. Okay, okay. Yeah, I haven't used a calculator for a long time. All right, so that's actually equal to 0. So, therefore, if that p over 1 is equal to 0, according to the factor theorem, x minus 1 is a factor. All right, and that's how you actually do this question here, by just checking if it's a factor or not. All right, so once we know that, if this if a certain term is a factor of the polynomial equation or function, then we can actually now be able to factorize a polynomial expression completely. Okay, if the question is designed where the polynomial expression can be factorized, then we should be able to factorize. All right, so how do we factorize? All right, there's one important concept that you need to know to factorize this. Okay, so basically I'm just going to write down the steps for factorizing polynomials. Okay, all right, we are going to use try and error method to find an integer 0. Okay, so the first step here is we are using a trial and error method, and I'm going to show you using one example what does that mean to find an integer 0. Okay, now the question is, how do we try? All right, and what number do we need to try? All right, so there's one very important message that I wanted to show you here is, if the coefficient, this is extremely important, I wish you actually write it down. If the coefficient of any polynomial expression here or integers, has to be integers, all right? It only works if the coefficient of p of x are integers. Okay, so extremely important. All integers. If one of them are not integer, then this is not going to work. Then all the integer zeros. Now, integer zeros just means that just means the roots or the solutions of the polynomial. All right, of px are divisors of the constant term. All right, so what does that mean? Okay, what does that mean, and how do we sort of using this idea to actually do the question? What I'm going to do is I'm using the previous example here to show you. So for example, this one here. Okay, I'm just starting on the next page. Right, so if we want to fully factorize this, expression here, how can I do it? Well, according to that, sentence, it says, if the coefficient of p of x are all integers, all right, all integers, then all the integer zeros, which means all the zeros, all the roots, all the solutions, just different words, of p of x are just the divisors of the constant term. All right, so it comes to this side. All right, now if we just pay attention to all the integers, okay, all the coefficient in front of the terms here, they're all integers. So that means all the zeros, all right, so all the possible value for x that makes the equation equals to 0 works is going to be the divisor of that -4. Okay, so therefore the first step is we're going to check the constant term. Okay, we're going to check the constant term, and then we are going to find out all the factors of that constant term -4 and list all the possible factors, including negative. So what does that mean is if the constant term is like a large number, then like for example 16, then yeah, well in that case it will be plus minus 1 and plus minus 2 plus minus 4. You're going to find all the factors until that's possible, right? And then step 2 is you're going to use factor theorem to check. That's why it's called like check, try and error, right? To check for integer zeros. All right, so if you would just look at this number here, that's minus 4, all right? With that minus 4, if we look at this minus 4, we can have plus minus 1 as the factor. We can have plus minus 2 as the factor. We can have plus minus 4 as the factor. So it's like, a worst case scenario is you check the first few times, none of the answer gives you the zeros, so therefore like you have to check all the possible, all the possible factors. But obviously, it's in the extreme, cases when you checked for the, for the first 4 times, none of the answer is the zeros. In that case, you're just very unlucky. All right. Usually, the question is designed where the first couple of times when you check the answers, you do get the answer straight away. Okay. So you always start with a small number. You always start with 1 and negative 1. That's all my suggestion. I want to give it to you. Always start from 1 and negative 1. So for this question here, what I want to do is just purely use this method, okay, to just check. All right. I'm not using any long division or anything to factorize this. Later, eventually, we are going to use a combination method, all right? So not just using this try and error method to factorize, we also need to properly incorporate long division to help us to factorize as well, okay? All right, so let's factorize this using the method we just learned, okay? So check. I will just write down P1 first, all right? Check 1. If P1 works, then x minus 1 is going to be a factor. Now, from the previous question, I think P1 works, right? So that gives you 2 minus 9 plus 11 minus 4, which is minus 7 plus 4. So that is equal to 4 minus 4, and that's equal to 0. So therefore, we can make a conclusion that x minus 1 is 1 of the factor. Which also tells you that, when x is equal to 1, it's one of the solution to this polynomial equation if we're making this one equal to 0. Okay? All right, after we finish checking the 1, now you check p minus 1. So you keep going, all right? You keep checking all of those until you have all your factors. Now, this is degree of 4. In the later topics, I'll talk about when it's the highest power is equal to 4, then you have a maximum of 4 solutions. So once you have all 4 solutions, you can stop. All right, p negative 1. So let's just do another substitution. Obviously, you don't have to write this in exams like, negative 1 to the power 4. You can just do the calculation all, straight away. I'll do it this way just because I want to show everyone this is the substitution here. Just by looking at this, I probably don't even need to use a calculator. It's not equal to 0. Okay, you don't need to really calculate the values. I don't care if it's equal to minus 2, minus 4, minus 5, minus 100. As long as it's not equal to 0, I don't need that number there. Okay, so once I finish 1 and negative 1, all right, so that one is finished. Now I need to move on to plus minus 2. So now you check plus minus 2. So you do P2 and you substitute. All right, so 2 to the power 4 is 16. That's 8 minus 36 plus 22 minus 4. 24 minus 36 plus 22 minus 4. Let's see if that gives me 0. Minus 4. Okay, it does not. It's equal to 6. So therefore, again, that is not the solution to this question there. So therefore, you can't answer it. All right, it's not the solution. All right, so nope, not P2. And we can continue the process by checking a P negative 2. As you can see here, this method works pretty okay, but still it takes a long time to check every single solution. I do have a better way to do it. Is actually, use a long division to help us to reduce the power from power 4 to power 3, and you check it again. But I'll teach you that later. All right. Okay, so that's negative 36 minus 22 minus 4. I don't think that's equal to 0. No, it's too, yeah, the numbers doesn't seem to be equal to 0. So as you can see, a long process. I've checked like 4 solutions already, and I still have 2 more to go, which is plus 4 and minus 4. But as I said again, usually I will use a combination of methods. So I'm just using this method as a demonstration purpose of to show you you can check every single one to try to find out all the terms, but there's also another issue later on, something called a double root. So which means like you can have like multiple roots where maybe 1 or -1 is a multiple root. So in that case, when you're using this method here, that checking is not going to help you because you will end up with just only one solution that's correct. For example, x minus 1 is correct. However, you can't use the checking to actually see if there's any other way or to actually get the answers. So we need to use the long division to help us. All right, so in this case, I'm going to use my calculator to work out the answer. All right, let's hope that becomes the answer here. All right, unfortunately, that's still not equal to 0. All right, so the last one. Oh well, okay, that takes long. Not an ideal way. All right, let's try it one more time this time. 256 minus 64 minus 144. Looks promising this time. Minus 44 minus 4. Okay. All right, that is equal to 0. Good. So therefore, we have another factor, which is x plus 4 is one of the factor. But then the problem here is this is a degree of 4 polynomials, right? So if it's a degree of 4 polynomials, we should have like 4 factors if you think about it, all right? However, we only have 2 factors right now. So which means one of the factor could be a double root or even a triple root in this case here. So we can have like a multiple of x minus 1 times by x minus 1 times by x minus 1. The only way you can figure out this is using either differentiation, which I will show you later on, and or we're using a long division. All right, so I'll show you how to do the long division. All right, remember at the end we just need to factorize this. All right, so previously we have already proved that x minus 1 is a root. We have already proved that, okay? So we also proved that x plus 4 is a root, yes? All right, so in that case here, the divisor could be just x minus 1 and x plus 4, which now we can expand, and that gives us this. Okay, so once we have this, then we can use the long division to work out this answer here. So that's x squared plus 3x minus 4. All right, so let's start using the long division to actually work out the answer. That's x to the power of 2, 3x to the power of 3, minus 4x squared. And that's minus 5x squared plus 11x minus 4. Minus 5, oops. That's just minus 5. Okay, so minus 5x squared plus... Did I do this question right? Okay, minus 5 plus 15x plus 20. I think I made a mistake again. Why am I keep making mistakes? Where did I make a mistake here? Oh yeah, I made a mistake because I didn't even subtract these two. Okay, all right. My bad. Okay, that's terrible. Again, shouldn't make that silly mistake. All right, my long division. I probably need to long division. Need to learn long division. Okay, that's minus 2x to the power 3, minus 5x squared plus 11x minus 4. Okay, minus 2x to the power 3, minus 6x squared plus 8x. I'm just going to slow it down. and do it correctly this time. Oh, almost another mistake. Okay, great. Plus 1. So x squared plus 3x minus 4. And then at the end, the remainder is equal to 0. Good. If the remainder is not equal to 0, that means the factors you find out is not correct. So now we have these two factors. Obviously, on this side, on the divisor side, we have x minus 1, x plus 4. Now, for the quotient, that's another formula, which is x minus, that's another like a perfect square formula, x minus 1 square. So therefore, we have some triple roots. X minus 1 is actually a triple factor, and when x is equal to 1, it's called a triple root of these polynomials. Alright, so therefore this polynomial px can be factorized in terms of x minus 1 to the power of 3 and x plus 4. Alright, and that's it for this answer here. That's all, okay? That's all you need to do to factorize and solve the equation. I'll do a question from the exercise, and I feel like this is enough for everyone to start with your work. Alright, so I'll just start with maybe this question. I'm going to solve x to the power 3 plus 3x squared minus 6x minus 8 equal to 0. Okay, how about this? Yep, okay, so to solve this one here, we are just going to look, first identify the negative 8 here. So you have many factors. We can have like plus minus 1, plus minus 2, plus minus 4, plus minus 8. But I just want to show you we're using a long division as well to actually factorize that instead of just purely relying on the factor theorem. Okay, so first step, let p of x equal to x to the power 3 plus 3x squared minus 6x minus 8. Now I'm just going to start to check. Check P1. 1 plus 3 minus 6 plus minus 8. That's not equal to 0, okay, unfortunately. Now you check P minus 1. Minus 1 plus 3 plus 6 minus 8. Okay, that's 8 minus 8, which is equal to 0. Okay, good. So that tells you that, x plus 1 is one of the factor. Alright, it's one of the factors. Now, once you finish that, I'm going to start to do long division. I'm not going to check it again. Alright, you can continue to check, but you can see from the previous examples, sometimes even you check everything, you probably have some double or triple roots there, and it's just going to take a longer time to find the answers. Alright, so long division is the way to go. So that's x to the power of 2. Alright, so 2x squared minus 6x minus 8. Alright, minus 8x minus 8 minus 8. Perfect. Alright, I do have a 0 at the end, and that's what you need. Alright, so therefore, your quotient here is equal to x squared plus 2x minus 8. So therefore, the polynomial function here is now be factorized into these two factors. And then the good thing about factorizing quadratics is everybody should know how to factorize using cross method now. So that's really easy to deal with that now. Okay, it's not hard anymore. Okay, so that's x minus 2, x plus 4. And that's it, fully factorized. So as you can see for the next two factors, x minus 2 and x plus 4, that means you can check, okay, you can check when, when that's p of 2 and this is p of minus 4. If you check these two, and it will give you zeros. But I just feel like a long division is quicker than just check every single possible answers there. All right. Okay, so that's all for this lesson. I hope that you understand the factor and the remainder theorem here. Again, if you have any questions, let me know. Thank you.